I'm hoping this works. Anyway, I just got an email from your union rep. No, actually, I'm just giving Paul a hard time. But anyway, he's saying, "Hey, we're struggling with problems 27 to 28. I haven't taught you yet. I haven't taught you that stuff. I jumped over this gravitational pull of things and went straight into the normal force and the static forces for actually the homework that's due a little bit later. Another thing, another one of your students um, sent me an email. She said, "Hey, how come the homework due on Monday is due at 2 p.m. and not 11:59 like the others?" Simple reason, I'm an idiot. I forgot to change the thing. So we'll take care of that. I've already taken care of that. So it's due at 11:59 now. So let's take a look at this gravitational thing real quick. All right. So here's the deal. I'm always saying that. Here's what's going on. Here's what Newton figured out. All right. Back in the day. Why isn't this coming on? There we go. Look at that. Look at that. All right. Now, take a peek. I've got an object, okay? And I got another massive object over here. The same laws, the classical laws of motion, the three laws of motion, guide our whirling planet. So there's a hymn that we sing in my church. It's God, you guide the whirling planets, and I always write in the program, no, F, this guides our whirling planets. F equals the force is equal to the gravitational constant G times the mass of the big planet times the mass of the little planet or satellite divided by r squared. And now you got to be careful. The r is the distance between the centers of them. All right, so when we're talking about the distance between, sometimes you can eliminate, this becomes inconsequential. And why is it r? R is not a radius. R, not a radius. Okay? Remember that. Remember that. So R is not a radius. It's a radial thing because no matter where the satellite is as it's going around the bigger body, the acceleration is always pointing towards the center. Thus, it's a radial vector that calculates that. Where G, okay, so G is equal to 6.67 times 10 to the negative 11 newtons per meter squared per kilogram squared. Okay, that's a gravitational constant. Cavendish gave this constant. Newton knew that it was there has to be a constant. He just couldn't calculate it down to this level. He didn't have the materials. He didn't have the technology to get it down. Cavendish did later on in like the 1860s. And Cavendish was actually the chair of the math and physics department at Cambridge University where Newton sat. All right. Anyway, so let me stop this video here. So this sets us up. Here's the equation you're going to use. The force equals that. And when we get into the next chapter, when we get into chapter 5, we're going to see that this is also, we can calculate the speed of how fast the satellite is going around there. All right? Okay, so let's just take a look. Let's just take a look at this real quick. Oh,